Well, it's great to be here. Today, I will like to talk a little bit about the project that has been going on for a number of years. This presentation is a little bit different than my normal presentations in the sense that I normally talk about a topic and I bring data from different projects to kind of illustrate the points. In this presentation, I will mostly focus on just one project. And so I'll go into a little bit more detail, perhaps in terms of the materials and methods of that project as well, so you can understand where the data is coming from. And I would like to acknowledge my co-author, Gabriel Payao. He earned his PhD degree doing this project. So most of the work that I am presenting is the work that he did. I would also like to acknowledge and appreciate the field crew. These projects take a lot of work, a lot of time, and a lot of funds. And so I appreciate the funding. This funding came mostly through the soybean growers, a little bit of money from AFREC, and like I said, the field crew was very instrumental in a lot of these measurements. So one of the things that we know is that over time things change in agriculture, not only in terms of tractors and equipment, but what we do with those pieces of equipment, how we do tillage, how we do different things. The other thing too that has changed and continues to change is climate. You can see here that we have over time in Minnesota, this is for winter temperatures, we have become warmer, and that trend continues upward. We have also become wetter as you look at across Minnesota from the late 1800s to more or less present day. We see this increase in precipitation. And these two things combined result in challenges for nitrogen management. Nitrogen and water, as we heard Vasu, go together, and we are doing a lot of research with that in the irrigation, but we are also looking at a lot of these things in dryland agriculture, because obviously we have more water, and with more water, it comes more potential for nitrogen loss, as well as with warmer temperatures, because a lot of these loss mechanisms are mediated through microbial activity. And because of these things, drainage is becoming even more important. Much of the fine texture soils in Minnesota are tile drained, but there are still a number of fields and areas that are not drained or don't have adequate drainage. They may be tile drained, but they don't have adequate drainage, or there are parts of the field that don't drain very well. And so drainage is certainly very important. When we have an undrained soil, we have a lot of water in the soil profile, and that results not only in plants not able to explore the soil profile very well, but also in terms of nitrogen loss, we can get issues with nitrous oxide emissions if we have saturated conditions. On the other hand, if we have tile drain, then we tend to increase the amount of nitrate that leaches below the root zone into a ditch that ends up into a river and into some body of water somewhere. In Minnesota, a lot of that goes to the Mississippi that ends up in the Gulf of Mexico and creates hypoxia. So there are trade-offs in terms of what tile drainage does, but it is a very important practice, especially as we get wetter. And then the other part is tillage, and tillage affects both the moisture content of the soil, and it also affects temperature. And in colder climates like Minnesota, this is very important for spring conditions, especially because we need to get the crops established quickly and establish them well in the spring. And so the more residue we have in the soil, typically the cooler and wetter the conditions are in the soil, and it can delay planting, it can delay emergence, things like that. So all of these things are very important things. And so this study, it's conducted in a farmer field near Wells, Minnesota, in south central part of the state, Waseca County. And it's a fairly large study for small plot research. We have 720 plots that they are 10 by 30 foot plots. And the way that the study is divided, we have blocks of drain and undrained conditions. So all of the field is tile, but some blocks have the tiles completely open, so those will be the drain, and some plots have them completely closed, so those will be undrained. And we have those replicated 4 times. And then within that, we have both corn and soybean crops present. And then we subdivide that into conventional tillage, strip tillage, and no tillage, as you can see here. And then within those, we have nitrogen treatments that go from 0 to 200 pounds of nitrogen so that we can have a response curve to nitrogen. And the additional subdivision in part of the study, as I will show you in a second, is pre-plant nitrogen rates and split applications, where we apply 40 pounds of nitrogen pre-plant, and then the rest of the nitrogen was applied as side dress around V6 to V8. And so with nitrogen management, one of the things that we wanted to see was, okay, we know that the nitrogen loss potential goes with the precipitation pattern. And so we know that those don't match very well with nitrogen uptake by the corn crop. Typically, we apply nitrogen early in the season before corn needs it, and at the time when we have a lot of potential for nitrogen loss. And so we are looking at applying nitrogen pre-plant early in the season when we have the most potential for loss. But we're also looking at a split application where we apply the majority of nitrogen at side dress, kind of after the highest period of potential for loss, but before the corn crop needs most of its nitrogen. And then for soybean, this is a question that always comes up, is do soybeans need nitrogen? And they do need quite a bit of nitrogen, but they fix their own nitrogen. But the question is, would they be benefited by having nitrogen fertilizer applied to them? So we have 2 different studies that I'll be showing here, where we looked at applying nitrogen at different stages, kind of early, mid, and later in the season. And then a different approach where we apply just one high rate of nitrogen at different stages through the growing season. And we'll talk about that in a second. In this study, we have done a lot of measurements. Today, we have simply no time to talk about many of these things. We have looked at nitrous oxide emissions. We have looked at soil moisture and temperature. We have looked at the mineralization of these soils, how much nitrogen is produced by microbial activity in the soil through the growing season. And we have looked at, in this article of Crops and Soils, how variable soil nitrogen is in the soil when we have drain or undrained conditions. And unfortunately, today we won't talk really about most of these things, but we'll talk about some other things, specifically the timing of nitrogen application and tillage, how that affects the drainage and tillage, how they affect timing of nitrogen. So what we have here is the different years from 2014 to 2019, and then the average. For pre-plant, PL is for pre-plant, and for split application in the blue. The next columns are the EONR, or economic optimum end rate in pounds of nitrogen per acre, for both the drain and the undrained soil conditions. And then the last set of columns is the yield at the economic optimum end rate for drain and undrained. And the beauty of having these studies over a range of years is that it allows you to look at what happens under different weather conditions. And this is very important because no year, we talk about average conditions, but there is no such thing. Every year is different. Every year brings its own set of conditions. And so it allows us to look at those things. This little graph here on the side is kind of for your information kind of thing. I don't expect you to pay too much attention, but it does show the water filled pore space, or the amount of water present in the soil throughout the growing season. The bars represent the precipitation events, and the amount, I'm sorry, this is in millimeters, not inches of water. And then these numbers here on the top represent the deviation from the average, from the 30-year average.
Can you imagine that? I don't know who this is. She's in the United Arab Emirates,
okay,
in Dubai.
We are hearing something here in the room
She's-
from somewhere else. I wonder if it's the room next door. All right, well, we'll continue. So the deviation in precipitation and then the deviation in temperature with the red values or the red boxes. And then you can see also there where we had the pre-plant and the split application and then planting and harvest, just to kind of give you an idea. Now in 2016, it was, as you can see here, fairly uniform precipitation for most of the growing season. And in that year, if we look at it, the environmental conditions were really almost near optimum for crop production in this site. And the undrained soils were just as productive and as profitable as the drained soils. So there was no much difference there, as you can see, for drain and undrained in terms of the amount of nitrogen and the yield that we obtained. Then we moved to 2018. 2018 was a very wet year, especially in the early part of the growing season, where in May and June, we have over 7 inches of precipitation above the normal, so extremely wet conditions. And in those conditions, then we see that the drained soils definitely were more productive than the undrained soils. We had excess water and drainage. That's why we installed drainage, is to get rid of the excess water. And the other thing is that is interesting, as you can see in 2018, is that the split application in those situations was better than the pre-plant application. Why? Because we are applying nitrogen a little bit later in the season. We still had potential for nitrogen loss, even with the split application this year because it was so wet. But we basically reduced the window of time for that nitrogen to be lost doing the split application. And then when we look across all of the years at the average or the mean, we find that regardless of the time of application, the undrained soils tend to need more nitrogen to optimize the yield consistently, or mostly consistently, and obviously across as an average, we need more nitrogen when we have undrained conditions than when we have adequate drainage. The pre-plant applications in general tend to be adequate for drained soils, but when we have undrained soils, that's where the split application has a higher chance of being beneficial. It doesn't mean that the split application will be beneficial every year, but it means that in general, you will have more chance of seeing a benefit from that split application when you have undrained conditions. And then here in the table below, what we are looking at is average across all of the years for the pre-plant versus the split application, the profitability. This is looking at the EONR, the margins at the EONR. So this will be 2020 vision, right? This is the amount that we calculated at the end of the growing season for that particular site. We knew exactly how much nitrogen it took to be profitable. And so when you look at this, you see that consistently the drained soil was more profitable than the undrained soil, regardless of when you apply nitrogen, whether it was pre-plant or split. Now, when you look at the other set of rows here, this is looking at the MRTN. So the MRTN is the nitrogen rate guideline that we have for the university. This is regional, it's more general. So the first set of columns is perfect. We knew exactly how much nitrogen we needed, but nobody does. Nobody knows how much nitrogen you need before the growing season is over. And so if you go with an estimate, which will be what the recommendation would be, you see that again, using the MRTN approach, you will be most profitable with drain than in the undrained conditions. And even more so because here you're trying to estimate what is the potential, and you see that the differences there become much larger. So following a guideline when you don't know for sure how much nitrogen you will need could be even more important in those conditions when you have uncertainty in terms of drain and undrain. The other thing that is really interesting about this study is that if you look here on the horizontal axis, we have drain and undrained conditions. So for each one of these, we have two sets of boxes. The green ones represent the pre-plant and the blue boxes represent the split application for the different years. Each one of those panels is a year from 2014 through 2019. And what we are really trying to look at in here is the comparison of the green box against the other green box or the blue box against the other blue box in there. And consistently every year, regardless of how that box looks in relationship to the others, you see that the undrained has a much bigger box than the drain, which is telling me that we have a lot more variability when we have undrained conditions than when we have drain conditions. So even if we would be able to manage things perfectly in both systems, the undrained conditions already from the get-go will be more challenging because you have more uncertainty. There are a lot of other things going on that make this system more variable, less predictable, more difficult to manage. And then combining the fact that we saw more nitrogen needed in undrained conditions, plus looking at kind of a budget, a relative budget of nitrogen in the soil. Here we are looking at the nitrogen uptake in the grain in red, the nitrogen uptake in the stover in the blue, and then the residual total nitrogen in the fall in the soil in the green box, in the green bars for the different nitrogen rates. So here we have pre-plant, PL is for pre-plant, and the different nitrogen rates from 0 to 220, 24 kilograms, 220 pounds. And then the split applications for those rates, where we compare drain and undrained. So if we look at the sets of bar within each of those nitrogen rates, drain versus undrained, consistently what you see is that the undrained soil had less nitrogen overall, counting what was in the grain, in the plant, and in the soil compared to the drain. So the fact that you needed more nitrogen with undrained conditions to optimize your yield, and that you have overall less nitrogen in that system when you account for all of it, is telling me that the undrained soil overall is losing more nitrogen than the drained soil. We know that we lose some nitrogen through leaching with the drainage, but in undrained conditions, in those conditions what we have with these fine texture soils in South Central Minnesota, we lose a lot of nitrogen through denitrification. And we've seen that through some of the studies of nitrous oxide emissions that we quantify that in previous years. The other thing that we looked at is how much of that nitrogen that is left over after the growing season may be available the following year. So here what you're looking at is in the horizontal axis is we equated the EONR, the economic optimum N rate, to 0. And then in relationship to that with the other nitrogen rates, so nitrogen rates that were below the economic optimum or above the economic optimum. And so we measure soil nitrogen in the fall and then the next spring in those same plots. And it doesn't show very clearly in here. I'll show you a better slide in a second, but in general, the split application tend to have more residual nitrogen than the pre-plant application. But the thing that I really want to focus my attention on in here is the fact that even with additional nitrogen above the economic optimum, that's where we start to lose more nitrogen because the plant is not using it. This starts to increase. Even with those situations where we have quite a bit more residual, when we go the next spring, this is flat. So whether you have 0 nitrogen or an excess of nitrogen, the amount of nitrogen present the next growing season is about the same. So as I always say, soils are not the best saving account for nitrogen. You just cannot hold that nitrogen in the soil. This is an schematic representing what happens with nitrogen management in terms of yield, profitability, and also nitrogen loss. So in general, what you see is as you increase nitrogen in the horizontal axis, your crop yield will increase to an optimum, and then it kind of plateaus after that. And then in terms of nitrogen loss, it will be fairly low. There will be nitrogen loss, even when you apply very little nitrogen, but it will be fairly low to about that optimum. And then past that point of optimum, since the plant is not using more nitrogen, it plateaus, you see this increase in potential for nitrogen loss. And that's certainly what we see in the field. This is just one example, one of the years that I am presenting here for 2016, in this case, drain conditions or undrained on the bottom graph. You see the yield with the red, the blue dot represents the economic optimum N. In this case, it was 91 pounds and it produced 216 bushels. In the undrained, it was 121 and produced 222 bushels. But you see that after that point, it's fairly flat. There is no more increase in yield. But then when you look at these other axes showing the total inorganic nitrogen, this will be ammonium plus nitrate in the top 3 feet of the soil, you see this increase in residual nitrogen. And if you do a calculation of the difference between the check and the economic optimum, the difference is about 0.11, whereas in here it goes to 0.29. If you look at the undrained, it goes about 0.2 versus 0.64. So the difference is substantial. Once you apply more nitrogen than you need, what you're doing is you're reducing your profitability because you're not getting more yield, and you're increasing the environmental impact or the potential for environmental degradation because of that nitrogen. And this is also depicted in here where we look at different nitrogen rates with drain and undrained conditions. The red is the fall, the yellow is the spring. In terms of nitrogen, as I showed earlier, this shows it more clearly that once you apply an excess of nitrogen, in the fall, you have a lot of residual nitrogen, but by next spring, those will be reduced substantially and about the same as you have for any of the other N rates. And I show a similar slide earlier where we look at the potential for nitrogen loss versus the curve for nitrogen uptake, and they don't match. And so this idea of applying nitrogen a little bit later in the season so that we minimize the potential for loss, but apply it early enough so that it's present for when corn needs to take it up. That works great in theory, but in the reality, we kind of see a different picture. And this is not from the study I've been talking about. There are a couple of slides I'll be showing you here that are from a different study, but I think they illustrate the point very well in terms of the potential for improving things when we split apply nitrogen compared to using a pre-plant only application. This study was a study that we did across the Midwest. There were 8 different universities involved in the project. The data that you see here is across 49 site years of data collected over a 3-year period. And what we have in here is we are comparing the split nitrogen application to a pre-plant only application. So let me explain a little bit what is going on in this graph. In the x-axis or horizontal axis, what you have is different scenarios where you have 40 plus SD means 40 pounds of nitrogen applied pre-plant, and then additional nitrogen applied at site rest around B8, B9. And S means single, for single application. So the 40 plus site rest, those rates, we had a number of rates, they will match the total amount of nitrogen applied pre-plant. So you're basically comparing if I apply 100% of my nitrogen pre-plant, or if I split apply with 40 plus the rest of the nitrogen later, whether that was the same, greater, or smaller. And then we also had some treatments where we apply actually 80 pounds pre-plant plus the site rest and compare that to a single pre-plant application. And as you can see, this is the percent of sites that show a significant response to these treatments. In this case here, you're looking at the site rest being equal to the split to the single application. 80% of the sites show no difference. So it was the same whether you were pre-plant applying or split applying nitrogen. You look at this one where we are comparing the 80 plus site rest compared to the single, same thing, 84% of the sites were the same. So there was no benefit to doing a split application or a pre-plant, it was the same. And then comparing here the 40 versus the 80 pre-plant, and then the rest aside rest, 97% of the sites. So basically, it doesn't matter how much nitrogen you apply. This was a question of, okay, if you are doing a split application, is 40 pounds enough, or do you need to apply more? And most of these sites work on after soybean. And it shows that with 40 pounds, if you're going to do a split application with 40 pounds pre-plant, you have adequate amount of nitrogen to hold that crop until you apply at side dress. But then there were a few sites where the side dress application produced lower yields than the single, and others where it was the opposite, where the split application produced slightly greater yields than the single application. And we looked at those in more detail. This was some of the work that one of my students, Jason Clark, did for his PhD. And what you see here is that when the split application was greater than the single application, it typically was sandy soils. So soils that have a lot of potential for nitrogen loss early in the season. And that's what we recommend, is that if you have a sandy soil, don't apply all your nitrogen pre-plant, because you're going to lose quite a bit of that. And then the amount of evenness of precipitation. So if you have more even precipitation, typically those sites tended to have a benefit with the split application over a single. But the sites where the single application was better than the split application tended to be sites with more finer texture soil, higher CEC, and early season warmer temperatures. Okay, again, not a huge number of sites, 6%, 14% of the sites show the benefit one way or the other. Most of them, it made no difference. And following that with, this is also part of that larger regional study. What you're looking at in here is the residual nitrogen. In the x-axis, 0 represents the economic optimum N rate. And so numbers, positive numbers mean more nitrogen than the economic. Lower numbers mean less nitrogen than the economic. And the responses that we saw in here, you can see that the dotted line here represents the split application, and the solid line represents the pre-plant only application. So as I showed earlier, if you apply more nitrogen than you need above the economic optimum, those numbers start to shoot up pretty quick. But the other thing that is interesting is that the split application actually had more residual nitrogen than the pre-plant application, as I show in the study that I've been discussing, but more clearly in this one across many site years. So you may think, well, so that means that split application is better because you end up with more nitrogen at the end of the season. Well, what is happening here is that you are losing nitrogen at different times. With the pre-plant application, you tend to lose nitrogen earlier in the season. With the split application, as I showed you earlier, you will not have that nitrogen the next spring. So it will be lost, but it will be lost later. And in terms of improving the efficiency with the time of application, this graph on the right shows that basically whether you were doing a pre-plant or a split application, those lines are on top of each other. There is no improvement in nitrogen use efficiency in terms of how much the plant used nitrogen with a pre-plant application or a split application. No difference in there. All right, so now returning back to the study I've been discussing. We've been talking mostly about drainage. The other component to this study was tillage. And so we have here in the horizontal axis, we have conventional tillage or CT, strip till, ST, and no till for the drain or the undrained conditions. And what you see very, very clearly here is that, well, as we said earlier, drainage makes a big difference. Drain soils tend to produce more yield than the undrained soils. But when you add the tillage component, strip till seems to work very well compared to a conventional tillage system. So the advantage here is that if you're looking at trying to do a conservation practice for tillage, strip till can do the trick. You don't have to do conventional tillage with strip till. You will get to about the same results as conventional. Not so with no-till. We see that no-till is very problematic, especially if you're under undrained conditions. That's kind of the worst case scenario because you have excess wetness, if soils are wet, cooler, and then you have all that residue on top of it. It makes it even worse. But the strip till seems to be a good alternative. And the differences were not as striking as with drainage. And the reason for that is explained here in these tables. When you look at the water field pore space, or the amount of water in the soil, there was a slight difference between tillage. Here I'm just showing conventional and no-till, which would be the extremes. There was a little bit better conditions for conventional than no-till, but no substantial. The drainage is where you saw the biggest difference in water field pore space. And then soil temperature, the same thing. There was a slight difference with the tillage, but the biggest difference was related to drainage condition. All right, so we've been talking only about corn so far. Let's talk a little bit about soybean. With soybean, here you're looking at drain versus undrained. That's what we have in the horizontal axis, and then in the vertical axis we have soybean grain yield for the different years from 2014 through 2020. And what you see is that basically there is no difference in yield with drain or undrained conditions in soybean in any of the years except in 2018, where we had very wet conditions. We had over 7 inches of above normal precipitation during May and June. And in that situation is where the drain was more, it was beneficial compared to the undrained. So soybeans tend to be a little bit more resilient to drainage. They don't seem to be as affected as corn. They tend to be just as variable as corn in terms of the drain and undrained. Under undrained conditions, we tend to have more variability in the yield, but the statistical differences are not there necessarily. And so overall, less responsiveness to drainage. We had 68 bushels with drain versus 67 bushels with undrained across, as an average across all of these years. And then looking at the effect of tillage, same thing. Soybeans don't seem to be very responsive to the tillage. You see the values there, pretty much the same yield, whether you have conventional strip till or no till. And then in terms of nitrogen management for soybean, we did two kinds of studies. The first part of the study from 2014 through 2016, we had treatments where we apply either no nitrogen or apply 40 pounds of nitrogen either at pre-plant, and I point those out in here. So we have the check here. The check, okay, something interesting. This is growing in rotation with corn. And so in the corn side, we have this treatment where we have no nitrogen applied to corn or soybean. So that's the 0. Then we have this check, which will be kind of the more traditional check that you will have in a commercial field, where you apply nitrogen to the corn crop to optimize the yield of the corn crop, and you apply no nitrogen to soybean. And then we had these treatments where we apply 40 pounds pre-plant to the soybean, 40 pounds at V4, 40 pounds at R1, or 40 pounds at R3. What we wanted to see here is if you apply nitrogen early in the season, we know that soybeans can become lazy and they won't fix nitrogen. So we wanted to see if you delay the application of that nitrogen until the R stages, the reproductive stages, will you see a difference, okay? And the bars, the red and the yellow is drained and the red is undrained. So I averaged them because there were no differences between the drainage here with these ladders on top. And so in 2014, what we found was that the check with no nitrogen yielded more than any of the other treatments with nitrogen application. In 2015, it was the opposite. The application of nitrogen, regardless of when you apply nitrogen, it didn't matter if you apply those 40 pounds of nitrogen pre-plant or at R3, they all yielded more than the check. And then in 2016, kind of no much difference there. Okay, so you have, take your pick. You have all the possible combinations there. Increase, decrease, no difference. Then in 2017 through 2019, what we did is something slightly different. Rather than applying nitrogen at different stages, but a small amount, we say, what if we just bombarded soybean with a huge amount of nitrogen so that if there is going to be a response to nitrogen, we will see it. In here, we were applying 120 pounds of nitrogen to soybean. I would not recommend doing that because it's not economical. But we were doing that and doing the application as a split. So we apply the 120 pounds, we divided into 3 equal increments and apply the first one at B4, the second one at R1, and the last one at R3. And we saw some, again, kind of the same thing where we saw some benefits in 2 of the years and no differences in 1 of the years. And again, when you put the economics, they don't pan out. It's just costs too much to, even if you do get a yield increase, it's pretty minimal, as you can see in there. And so here it's kind of across all the years, looking at with or without nitrogen. And you can see the spectrum as I show. Sometimes increases, sometimes decreases, sometimes makes no difference. But overall, when you look at the yield increase, it's just not profitable to apply nitrogen to soybean. And some of these years, as you can see, they were, pretty decent soybean yields. So wrapping it up, in terms of corn, some of the things that we learned through this project is that drainage is definitely a very important component in nitrogen management for corn. You have to kind of keep that in mind as you manage nitrogen. With drainage, we reduce the amount of nitrogen that we need for the corn crop. We increase the yield relative to those undrained soils. And this is especially true in wet years, in wet conditions, or with warmer springs, where again, you have typically more potential for nitrogen loss if you have undrained conditions. The undrained soil, the split application seems to be better for those conditions. So if you have a soil that is poorly drained, that doesn't have adequate drainage, the split application doesn't mean that it will pan out every year, but you have a better chance of seeing a benefit by split applying nitrogen in those situations. Simply why? Because again, with those undrained conditions, you have more potential for nitrogen loss early in the spring. But when you're looking at drained soils, we find that, as I mentioned earlier, the pre-plant application seems to work just as well. You don't really need to be split applying nitrogen because most years you will not see a benefit. Strip till is a viable alternative to conventional tillage. Both conventional and strip till seem to work very well. Where we do see a yield decline is in no-till, and especially if you have poorly drained conditions in the field. And the reason for tillage not being perhaps as important is because it seems like the drainage conditions of the soil kind of overshadow any effect of tillage in terms of the amount of water and the temperatures that we see in these soils. And then for soybeans, we see that they are not as responsive as corn in terms of the drainage. We do see a benefit with drainage when you have excessive precipitation. But in that study, in only 1 year out of all the years we had the study, we saw a benefit. So less influenced with drainage. The time of application, if you're applying nitrogen, I would say don't do it. It's not profitable. And as you saw, it's anybody's guess whether you will get a response or not to that nitrogen. Even if it's a large amount of nitrogen or a small amount, it really doesn't matter, or when you apply that nitrogen. And then the other part is that nitrogen management in the previous corn crop does not affect nitrogen status for the soybean crop the following year. The same could be said about, which I did not show in this presentation, the other way. If you apply nitrogen to soybean, would that affect the next year's corn crop? We see absolutely no benefit with that, because as I show with the soil data, any nitrogen that is left over at the end of the season is not going to be there the next year. And then looking ahead, this study is still ongoing. We just received funding from AFRIC to continue to look at some things. In addition to all these variables that we talked about, we dialed back a little bit in terms of how many nitrogen rates we have in there, but we are now adding some components of corn residue management, where we are adding a cover crop, no cover crop, so basically what we have up to this point, and then one residue management where we are actually removing a portion of the crop residue, of the corn residue out of the field to look at those dynamics in terms of soil health, in terms of nitrogen cycling, and what happens with the different drainage and tillage components in this study. So that's what is coming up. I know I cover a lot of the information. I put here a list of the publications that are either already published or in preparation, just as a reference for you. And if you have any questions about any of these later, I will be happy to share with you more details on this study. With that, I will stop and try to answer any questions. All right, I will start with the online questions here. The drain soil appears more profitable. I am assuming this doesn't account for end loss and environmental impacts. Should that cost be factored into cost? Very good question. What I think this study highlights is the fact that we do pollution trade-offs. Every time we do something in the field, what we are doing, I mean, obviously we are trying to improve it so that we improve productivity or reduce nitrogen loss or both. But typically what ends up happening is that we do some kind of pollution trade-off. Because with the drainage, what you're doing is you're increasing the potential for nitrate leaching. But if that soil doesn't have adequate drainage, what we see, and we saw that very clearly with the data in this study, is that you end up losing more nitrogen through denitrification, producing a greenhouse gas, N2O, that is 300 times more potent than CO2 in terms of global warming potential. So yes, you're reducing the amount of leaching, but you're increasing substantially the loss to the atmosphere. So, and this is certainly something that people that are focused more on regulation and environmental impacts are looking at, because ultimately is some kind of trade-off. And then you have to look and see which one is the least of two evils. Is it reducing leaching? Is it reducing denitrification? And what is the impact with yield? When you look at the yield, also, if you look at in terms of efficiency of improving nitrogen use efficiency, you see that the drainage increase the nitrogen use efficiency. And so that could be beneficial. Could the slow release end source be a good management tactic to mitigate the issue with undrained soils? Certainly. This is a really good question. I am actually doing a study right now. We started the last growing season looking specifically at control release polymer coated urea in these situations, because I have seen in other studies kind of as a small subset of treatments that there is a potential for benefit when you do use some techniques like these, where you basically you apply nitrogen early, but because of the coating, you're protecting nitrogen from loss early in the season, and then it releases in time for the crop. So more on that later, but I can see that there are some potential benefits in there for sure. Are these studies suggesting that nitrogen can only be credited for the current year and we should not focus on it going into the second season? Yes, unfortunately, that is the case. This is, of course, short term, okay? There is no way to measure these things unless you do these studies for a very, very long time, where if you are over applying nitrogen consistently, are you building up your soil organic matter or the potential for nitrogen cycling? Because we normally talk about these things as being gone, like nitrogen is lost. Well, not necessarily. Some of that nitrogen is cycling back into the system to produce a reserve of organic nitrogen. But in the short term, it's extremely hard to quantify that. What I would say though is that over applying nitrogen as a technique to, to store organic nitrogen for the long term is not a good alternative financially, because you're going to lose money every year, and environmentally, because the potential for loss, as we saw in this and many other studies, shows that if you're over applying nitrogen, you end up losing nitrogen. Yes, Pasu. Yeah, the question was that that the coming study incorporating cover crops, if it will be, if that's the purpose of that, is to look at kind of the nitrogen cycle. And yes, that's exactly right. With this, looking at residue management, we know that residue management is also impacting nitrogen cycling. And so we will be looking intensively at some of these components of the nitrogen cycle. when you have these systems in place with cover crops or residue removal or no removal, seeing what happens to the nitrogen cycling and the need for less or more nitrogen through fertilizers. All right. Other questions in the room? Bruce, can I continue answering these questions? Or... Okay. All right. When there are drained soils, is a pattern tile or any type of drainage system determine the classification? I am not quite sure how to answer this question. The study here was a very intense style. So what I would say is within fields, we know this. I mean, especially in wet years, it becomes very apparent that there are fields that have tile installed, but inadequate amount, or it's not installed correctly, or it has been damaged over the years. And so, again, I don't know if I answered that question, but yes, there is a problem there. We see that again in wet years where even if it's tiled, if a field is tiled, we see areas that have problems in them. And it's I think one of the most profitable things that we can do in terms of making sure that we minimize those areas where we have poorly drained conditions. So for the other questions that are online, I will try to answer those in the chat box later. So thank you very much.